Okay. Okay, sorry for that. The presenter will be Robbe Greef from the Vrije University, Brussels. Okay? Okay, thanks.
Thank you very much. Hi everyone, today I'm going to be presenting our work on a macro-aware C to Rust transpiler. So first a bit of context. This work is part of a larger project called Forces, where we're trying to build an incremental C and C++ to Rust transpiler, while really preserving readability and maintainability. And the transpiler project itself is also very focused on secure robotics and embedded systems. So there are some transpilers out there. C to Rust is the most notable of which. Also the only actively maintained one. But since our emphasis is so strongly on readability and maintainability, things like preserving comments and preserving macros is really important. And the latter part is what this project is about. So the preprocessor, what's the deal with this? So the preprocessor is a step, as the name implies, which occurs before compilation. And essentially it will expand some preprocessing directives into the source file and then pass it on to the compiler. And these preprocessor constructs are not actually part of C, and that's really important. And that means that we have to run the preprocessor to be able to have a file which we can parse and which we can even transpile. So then you might be asking, why don't we just run the preprocessor and transpile the produced C? Well, this is an example of a program we'll see in a bit, which is just skips white space. But unbeknownst to you guys, this actually uses 4 macros. And if you throw this through a preprocessor, you will get something like this, which is obviously not that readable, even in the C code. So it's obvious we want to retain these macros, but how do we do this if we actually have to run the preprocessor? The idea or process is called macro contracting, and essentially we're going to be running the preprocessor and then looking at the code and retracting or contracting any macros which we encounter back into invocations. Now obviously that's not possible for each macro. So for example, here we have a C file which redefines some syntactic constructs, and very obviously some of these constructs, such as the braces, are not able to be transpiled because Rust does not allow macros like this. Rust has much more structure, and the only macro which we actually would want to maintain here is the double macro. So something like this would be an ideal transpilation, where only the double macro is retained and the rest is obviously not in the code. So if we have a process of keeping macros, how do we decide which macros we want to keep, which are transpilable and which aren't? When looking at a program called Figlet, which is an ASCII text generator and just one of the first targets for a transpiler, we found that the majority of macros are essentially expression-like macros. And as in Figlet, over 70%, and it really depends on the code base, but generally over 70%, sometimes over 80% are expression-like macros. And so it's a really nice target for transpilation. Generally also, expressions have a pretty nice analog in Rust and are a bit more reduced in scope than saying all statements of C. So now that we know which macros we actually want to retain, how do we transpile a C macro to a Rust one? Essentially, there's one really big problem, which is that C macros are textual based. They are just token replacements, and from that some other problems arise. The first one being, since it's just tokens, it doesn't have any notion of syntax, essentially. And so that makes it really hard for us to reason over the macro, because it has no structure. C macros are also, again, tokens, so they're unhygienic. They have no notion of scoping, which means that like scoping issues or naming issues are definitely prevalent. And then finally, a bit for all macro systems, actually, macros don't really have any typing info. You don't know what goes in, you don't know what comes out. So again, reasoning over macros is very difficult in that way. And the first problem of not having any structure is actually solved by only retaining expressions, because we can just parse the macro body as an expression, and then we can reason over that. For the unhygienics, here's a small example of the things that can happen. So in this case, we have a macro called store copy, which invokes the store copy function in C. And if you throw this program, if you use the macro and you throw this program through a preprocessor, you'll get something like this, which is what you would expect. Store copy is being called, and as you want, store copy points to the real store copy function, and this will work as intended. However, if you for some reason have a symbol defined in some scope which shadows the outside identifier, in this case store copy in a local variable, then if you throw this through a preprocessor, the store copy will be replaced, but now it'll point to the local binding instead of the globally one. and that really results in not happening what the programmer intended. And so the solution here is pretty simple. At each macro invocation site, we check if those shadowing issues occur, and if they do, we throw a warning in the transpiler and we expand the macro because there's nothing we can do with this. And finally, the latest and the biggest issue, not having typing info. So first, a bit of information about C. If you may or may not know, C does do many implicit promotions. So for example, you can easily assign an integer to a short because C will just implicitly inject a cost to a short. It also happens in arithmetic. It happens basically everywhere in C. Now, in regular code, this is easily solved because if you just map the C code one-to-one to Rust, you can analyze the types and inject in Rust you would get an issue because in Rust you can't add an I32 to an I16, but then we can analyze the types and we can just inject the cost, which will give us the same semantics as C. Now, the problem arises when we wrap this addition in a macro, because now, again, we'll get a mismatch in Rust because we're still trying to add an I32 with an I16, but since this issue occurs in a macro, we don't have any typing information to fix this. And so these types of things happen everywhere in C, and so we have two solutions. The first one are helper traits, and the second one are passing in type parameters. A small thing of note is that the helper traits were not discussed in the paper. This is a work in progress, and that's this work that has progressed. So helper traits, the idea is that we generate a trait, and then we generate with, in this case, adds with the method add, and we generate an implementation for each, for all addable traits, so for all addable types. So I32 for I16, I32 for I32, all those kinds of things. And then instead of using a regular addition in a macro, we can just invoke the method, and Rust itself will just use the right method, and we will get the promotion, the implicit promotion which we wanted. The next issue, for example, in assignments have the same mechanics. So again, you can't assign an I32 to an I16, and we can't also create a trait for this, obviously. So the solution here is to actually do what we do in regular code and inject a cost, but now the transpiler will calculate a type at the invocation site and pass it in through the typing arguments in a Rust macro. So then we tied everything together and we started transpiling some code. So we transpiled Figlet. So as I mentioned, it's an ASCII text generator. We transpiled all but one file. That one file wasn't really important to macros. It was more of a limitation of the transpiler. And we found that we could retain 46 out of 85 macros. And that's pretty good. The example from earlier was also from Figlet. So here, if we throw this through our transpiler, we'll get something like this. I highlighted the macros for you. They're here. They're still retained. Obviously, there's a lot of type parameters which are generated, and so that's future work for us where we're going to be trying to clean those up as much as possible. Generally, the majority of these are able to be removed and are redundant. So that's a nice feature to look at. There's a lot more which we couldn't talk about in this presentation, so I suggest you read the paper if you want to know more. And finally, I'm going to be leaving you with a small demo. So here we have a program which you might know, Doom, the source code of Doom. This is the main file of Doom, and it's a C file as you'd expect. My PC, okay. So we can transpile this using our transpiler. So if we just go ahead and do that. Oh yeah, sorry. We can just transpile it. This will transpile the D main file. We can then, if we take a look at, if we take a look at the source codes side by side, here we can see that, for example, the set game description here, it uses a macro called a logical game mission, and I actually also transpiled this using C2Rust, and as you can see, C2Rust, this is all expanded. In our transpiler, it is not. We can then go into our Doom RS. We can build this. There are quite a bit of warnings, but that's not important. And then finally, we can build Doom itself. So that will be me. And this will link our generated library with Doom and obviously ignore the dmain file. And then finally we can run it and we get the Doom you expect. All right. That was it.
Okay, thank you for the great talk with the demo. Okay, so I will get the last question today. Oh, okay. So you need to talk to the microphone for YouTube.
So very great work. So I'm curious about one thing is, so is your implementation based on the C2 translator, or is it completely separate? Because it seems some of the unsafe code features, seems C2 is already supporting those. So implementation-wise, is it on top of the existing C2 Rust
This
compiler?
is a completely custom transpiler, yeah.
Also completely built from scratch?
Yeah.
So basically, but like, do you think it's possible to reuse the existing C2 Rust compiler classes?
For this work specifically, like the macros, most likely. The reason we didn't is because it's part of a larger project and our goals are a bit different than those of C2 Rust, so it made more sense for us specifically to build our own transpiler. I also think that our own transpiler has an architecture which is quite interesting and quite nice for academia in general, because it's easy to test things out, which might be more difficult with something that exists like C2 Rust.
Yes, agree. But like, for example, I think the C2 Rust compiler is kind of robust. It supports, for example, GoTo or like some very weird features. And because to ensure functional correctness is very hard in those cases, right? So what is currently, are you also replicating the same strategies, or you're taking some shortcut? Means it does not actually guarantee semantic equivalence in quantum cases.
As you mean with like formal verification, no. But this is the idea is that it would be semantically equivalent, yeah, of course.
Oh, okay.
Thank you. Any more questions? Okay, thank you for the good talk.
Thank you.
And this is, thank you. And this is the end of today's schedule for the LCTS today. And we will have lots of the great talks similar to today's talks tomorrow. So let's see you tomorrow. Okay, bye. Thank you.